Hello, this is the Project 2 video for Parker Brandt and Landon Perez for Dr. Osbay's Fluid Mechanics class in the summer of 2025. Today we are going to be simulating a laminar airflow across a flat plate. First thing we're going to do is come over here to the left and drag Fluid Flow Fluent into the project schematic, and we're going to select geometry, and this is going to be a 2D simulation. We're then going to right click on geometry and select New Design Modeler Geometry. Once that opens up, we can create our sketch. We're going to select Rectangle, and I'm changing my units from meter to centimeter. Come down here, create some dimensions. My length is going to be 1 meter, and my height is going to be 10 centimeters. Once that's done, we can come up here to Concept and create a surface. Click Generate. And then we can go back to Workbench. We can right click on Mesh, select Update. And once you see the check mark, you can double click on Mesh. Okay, come down here and you can see our sketch. We're going to right click on Mesh, Insert, and we're going to start with a face mesh. So we're going to select our geometry, come down here to Geometry and click Apply. We're then going to select Insert, and we need to control the size of our divisions. So we're going to select Sizing. We're going to come up to the top, select Edge, select the top wall, hold Control, and select the bottom wall. Click Apply. And we're going to change the type from element size to number of divisions. And I'm going to do for this 100 divisions. And we're going to change capture curvature from yes to no. And then we're going to change the behavior from soft to hard. And then we can click generate. And you can see the mesh. We need to create more sizing meshes. So we can create a gradient at the bottom to capture our boundary layer. So we're going to right click on mesh. We're going to do sizing again. And we're going to select the left wall and the right wall. We're going to do apply. And we're going to change the type to number of divisions. And I'm going to do 60. Capture curvature to no. And behavior from soft to hard. Now for this, because we want to create the gradient at the bottom, we're going to create a bias. So the divisions are more spaced out at the top and less spaced out at the bottom. That way we can create a gradient. So we're going to come down here to bias type, and I'm going to select the first one. And my bias factor is going to be 40. And then we're going to come over to the right, and we need to reverse the bias because you can see that at the top it's reversed. It should be the other way around. So I'm going to select reverse bias, select this edge and click apply. And now you can see they're both the same, and we can click generate. And you can see our new mesh. Next, we're going to name everything. So we're going to click face, and you can just click the geometry. Select it, and then right click and create name selection. Nope. This is going to be my airflow. And then edge. This is going to be inlet. Bottom is going to be our plate. The right is going to be our outlet. And then the top, you can name whatever you want. I'm just going to name mine pressure field. And once that's done, you can come over to the left, and if you click on the plus next to name selections, you can see everything. So once we create our mesh, we're going to go back to Workbench, and we're going to right click on setup, and we're going to select update. And once that's done, we can left click on setup. And we always do double precision, and I'm changing my processes to 8. This will depend on your computer. So you can see how many processes you have in Task Manager, I believe under Performance. Okay, so once this opens up, our type is going to be pressure based, and we're doing a steady 2D laminar flow. So this should be selected as planar, and then this should be absolute. The first thing we're going to do is select models, and we're going to change this to a viscous laminar flow. Select OK. Once that's done, we're going to come down here to materials, double click on air, and I'm changing my density to 1.2, and my viscosity is 1.8 times 10 to the negative 5. Okay, once we're out of there, come down here to cell zone conditions. Yep, that's okay. we're going to go into boundary conditions, and the first thing we're going to do is double click on inlet, and I'm changing my velocity to 2 meters per second. Double click on this. Yep, it's okay. Outlet's okay. Double click on plate. And we have a stationary wall with no slip condition. That's good. And we're going to right click on pressure field, and I'm changing the type to symmetry. That's all good. And if you double click on reference values, then you're going to change compute from inlet. And these values should match what you entered, the density, velocity, and viscosity. And then we're going to come down here to initialization. Hybrid initialization is fine. Actually, open up monitors and double click on residual. And you can change the convergence. So, for example, I'm going to do 1 times 10 to the negative 6. Iterations to plot, that's all good. Okay, and then we're going down to initialization, and hybrid initialization is fine. This coupled is fine. Second order upwind. Okay, back to initialization, and we're going to initialize it. And then we're going to go down to run calculation, and just change your number of iterations to a large number, so 1,000 or 10,000. And once that's done, you can select calculate. Okay. So to analyze your data, you can either do it in this program, or you can go back to Workbench and double click on results. And that'll open up CFD post where you can analyze your data. I find it easiest to create the velocity profiles in CFD post, and then getting your drag coefficient and your skin friction and your wall shear stress graphs, it's easiest to do in the Fluent program. So I guess we'll start with the velocity profiles. So if you come here to the CFD post, we're going to create location. I guess line 1's fine. So this first line is going to be at 35 centimeters. And you can see our line here. And then we're creating a second line, and it's going to be at 75 centimeters. And you can see our other line here. Then we're going to go to chart 1. I'm going to name it velocity profile. And go to data series. You can name this whatever you want. I'm just going to do 35 centimeters and then create a second one It's going to say 75 centimeters and change each location accordingly and clicked apply. That's why. Change the x-axis to velocity and the y-axis to y. And you can change the title if you want. It's fine. Okay. And here's your velocity profiles at the 2 different points. Now going back to fluid flow, fluent, we can get some of the values we need. So if we go down here to report definitions, click new, force report, drag, and make sure drag coefficient selected, and then the zone is the plate. Print to console, and then select compute. And down here in the bottom is your drag coefficient. So to create our contour, we're going to come down here into graphics, and we're going to create a velocity contour. We're going to save and display. Select close, and from this contour we can see the creation of our boundary layer. If we want to create a vector field, then we come down here under vectors, double click it, airflow, and we can create a vector field. And if we zoom in on our boundary layer, we can see it better. So from here, if we want to create plots of our wall shear stress or skin friction coefficient, then we're going to double click on XY plot. And we're going to select wall fluxes. And for wall shear stress, we would just create or select wall shear stress. X wall shear stress and wall shear stress should give you the same graph. But in any case, we will only see the wall shear stress across the x-axis, across the flat plate. And surface is going to be the plate. Select save plot. And then this will give us our position versus wall shear stress XY plot. If we want to see our skin friction coefficient, we just go back to XY plot, and we're going to select wall fluxes, and down here is skin friction coefficient. Same thing across the plate. Save. And we're going to get a very similar graph. Finally, if we wanted a contour plot with velocity vectors, then we're going to come over here to CFD post. We're going to create a velocity contour. And it's going to be from our inlet. No, it's going to be from our symmetry. And we're going to select apply. Oh, I accidentally made it pressure. It should be velocity. So here's the contour. Same contour as we made before. We're going to come up top to vectors. And we can just name this velocity vectors. Select OK. And you can select where you want these vectors to come from. I'm just going to do the outlet, but you can create lines. For example, we created line 1 and 2. So if I select line 1, which is what, where was it at? I believe that was at 35 centimeters. And 3D, and yeah, we're going to change the color. Just make it black. Need to switch it to constant. There we go. And here's our vectors. And this is a much better representation than at the other line. Finally, if we wanted a contour plot with velocity vectors, then we're going to come over here to CFD post. We're going to create a velocity contour. And it's going to be from our inlet. No, it's going to be from our symmetry. And we're going to select apply. Oh, I accidentally made it pressure. It should be velocity. So here's the contour. Same contour as we made before. We're going to come up top to vectors. And we can just name this velocity vectors. Select OK. And you can select where you want these vectors to come from. I'm just going to do the outlet, but you can create lines. For example, we created line 1 and 2. So if I select line 1, which is what, where was it at? I believe that was at 35 centimeters. And 3D, and yeah, we're going to change the color. Just make it black. Need to switch it to constant. and here's our vectors. And this is a much better representation than at the other line. And I believe that'll be everything. So thank you for watching.